Before I start, I'd like to expand on what Sunil said about the content of my lectures. First, for those of you that are taking research, there's a de minimis amount of physics on your research exam, direct physics. I don't take what I do lightly. However, the physics stuff is pretty much standard. It's not sophisticated. The examiners they understand that the way the physics works and the way it's presented can't be advanced physics, it has to be basic physics. So I really am presenting what you need to know. If you feel comfortable with this stuff, you will get enough physics questions right that you'll sail through that part of the test, and that stuff will not affect your score. And that's my goal. You know, to sit there and to invest 5 times as much time for a couple of extra points just doesn't make sense. I lecture at Texas Heart, that's where my faculty appointment is, and other places, and you know, it's just a bad investment strategically to get into too much stuff on this. And people get nervous about it, but you know, you're not gonna get any. If the examiners put hard stuff on the boards, you're not gonna get it right, nobody else is gonna get it right, it doesn't make a difference. So that's sort of my philosophy, and no one's come up and sort of yelled at me in the past number of years about it, whether it's in my own institution or others. Okay, let's talk about Doppler. Essentially what happens is this. An ultrasound transducer sends out sound. If those sound waves hit blood cells that are moving towards the transducer, the reflected frequency is higher than the transmitted frequency. Along the same lines, I don't want to do that, excuse me. If red blood cells are moving away from the probe, the reflected frequency is lower than the transmitted frequency. So there seems to be a change in frequency based on whether the source of the sound and the receiver are moving closer together or further apart. We know that. If you're standing on the beach and you run rapidly to the ocean, you'll be struck with a higher frequency because you're running into the waves. If you're waist deep in water and you run rapidly toward shore, you'll be hit with a lower frequency because you're running away from the waves. That's exactly what's happening here. Now the change or the difference in the frequency is called a Doppler shift or the Doppler frequency. Now the units of the Doppler shift are units of frequency, hertz, and what is the event? Cycles per second. But the transducer frequency is ultrasonic. We know that Doppler is audible. What do we hear? So the Doppler shift is audible, but the transducer frequency is ultrasonic. So what happens is this. Let's say you have a 2 megahertz probe. Sound goes out at 2 million cycles per second. Blood cells are moving towards the probe. The reflected frequency may be 2,008,000 cycles per second. That too is ultrasonic. So what goes out is ultrasound. What comes back is ultrasound. But the difference between 2,008,000 and 2 million is 8,000. So essentially the Doppler shift rides on top of the transducer frequency. Sometimes that's even called a carrier frequency. And it's extracted by a process called demodulation. Here is the Doppler equation, okay? It's in your notes. I'd like you to know it, okay? Basically, what do we have? The Doppler frequency is related to what? The speed of the red blood cells, right? That's important, okay? And it's inversely proportional to the propagation speed, which is a constant. So what do we have here? We have two things. The Doppler frequency is related to the speed of the red blood cells. That's what we're looking at. But look at this little demon here. The Doppler shift depends on the frequency of the transducer. It's actually a percentage of the transducer frequency. And that's an important fact that we'll get to a little bit later. Why is there a 2 in the Doppler equation? Because there are 2 Doppler shifts in the way we do it. The first Doppler shift is when the transducer is the source of the sound and the red blood cell is the listener. That by itself creates a Doppler shift. But then a reflection is created. It's as if the red blood cell becomes a source of a second wave. And then that wave experiences a Doppler shift as the red blood cell being the source and the transducer the receiver during reception. So our Doppler shifts are double. Our Doppler shifts are double. Now this is what we normally see. Doppler shift. When blood cells travel faster, we have a bigger Doppler shift. When blood cells travel slower, we have a smaller Doppler shift. And that's what we're banking on. But look at this. These patterns are the same. But this has to do with transducer frequency. With a higher frequency probe, my Doppler shift is bigger. With a lower frequency probe, my Doppler shift is smaller, because the Doppler shift is a percentage of the transducer frequency. So the Doppler shift can change, and actually does change, based on what frequency transducer we're going to use. Now, of course, when we use the Doppler equation and we program it into the ultrasound system to calculate the velocity, that will go away. So the Doppler shift that creates that velocity will change, but the velocity will still be measured accurately. And there's an important distinction that we'll get to a little bit later with that. And then cosine of the angle, we'll get to that in a minute as well. So what does Doppler measure? Doppler measures velocity, not speed. So there must be a difference. Speed is a magnitude, like 60 miles an hour. Velocity is a vector. It's a magnitude and a direction. So only the velocity component parallel to or along the ultrasound beam is measured by Doppler, which means we measure 100% of the true velocity when blood cells are moving directly towards the transducer or directly away. But if there's an angle between the direction of sound and the direction of flow, we measure something less than the true velocity. And what we measure is related to the cosine of the angle between the direction of flow and the direction of sound. Every angle has a cosine, just like every house has an address. So in order to calculate a velocity accurately, we need to know the angle. So this is a cartoon, or animation, shows a pointer that's spinning around. In the top part of the animation, we're looking at the pointer from above, and it's always its true length, because we're looking at it straight down. But when we look at that pointer on edge, the apparent length of the cursor changes based on which way you're looking and which way it's pointing. And that's what happens when we measure Dopplers, is the bottom. So the velocity seems to change based on the angle between the direction of sound and the direction of flow. This is in your notes. Here, red blood cells are going up and to the right. That's the true velocity, is the red arrow. The sound beam is going directly to the right. So here we see an angle labeled theta between the direction of flow and the direction of sound. And that means we're only going to measure the percentage that is equal to the cosine of that angle. And we see that the yellow vector is materially shorter than the red vector. And here are cosines. So cosine of 0 degrees is 1. I told you that. I told you that already. When you have no angle, you measure 100% of the true velocity. Well, let's go to the other extreme. What's the cosine of 90 degrees? It's 0. Big deal. That is a big deal. Why? Because we do duplex imaging. The best angle to get a reflection to make a picture is 90 degrees. What kind of Doppler do we get at 90 degrees? Nothing. The most accurate angle to do Doppler is 0 degrees. But that's like looking at the edge of a mirror and trying to make a picture. So Dopplering and imaging hate each other. And you'll see tables in your book later on in your notes that compare Doppler and imaging and CW and pulse Doppler. That's gold, right? Yeah.
You lost your...
I think maybe came in.
Oh, I'm sorry.
There you go.
Thank you. Okay, so the cosine, again, of 0 degrees is 1. Awesome for Doppler. No Doppler at 90 degrees. But we get great imaging. So imaging, Dopplering hate each other. All right, now, when we talk to vascular people, and some of you have vascular labs, everybody uses 60 degrees, but that's just a cult, and we don't have to worry about that. Let's look at 10 or 20 degrees. At 10 degrees, we measure 98% of the true velocity. 20 degrees, 94% of the true velocity. So as long as we're plus or minus 20 degrees, we don't have to do anything. That's such a small error that there's no need to worry about it. Once we get at angles more than about 20, 25 degrees, we should at least be cognizant of the fact that we're getting something less than the true velocity. Now, there are two basic forms of Doppler, continuous wave and pulsed. Let's talk about CW first. With continuous wave Doppler, you need two crystals in the probe. One is constantly talking, the yellow one, so we need a second crystal, in this case the red one, that listens. The beautiful thing about continuous wave Doppler is that we can measure any velocity accurately, no matter how high it is. The shortcoming with continuous wave Doppler is that when someone asks us where exactly are the red blood cells that created this Doppler shift, the answer is we don't know. It's anywhere in the region of overlap between the transmit and the receive beam. And that is a special name. It's called range ambiguity. Well, range in ultrasound means depth, and when something is ambiguous, it means you don't know. So range ambiguity simply means depth. I don't know. And that's the limitation of continuous wave Doppler. Now, one time somewhere, a long time ago, someone described to me continuous wave Doppler as a jet sniffer. And that's what it does. You know, you have a long region of overlap, so you take your CW transducer and you sort of sweep it around, and you measure the high velocities, and you know at least there's a high velocity in that region of overlap wherever the beam is going. So it sniffs out high velocity jets. So this is a brilliant slide that David Adams and Joe Kislow made a couple of years ago, right? Let's look at this. So what do we have? Here is continuous wave Doppler. Where are the red blood cells that created these Doppler shifts? Anywhere and everywhere in the region of overlap between the transmit and the receive beam. And here we're measuring velocities of 4 meters per second. That would be very, very high, and Pulse probably couldn't do it. The reason why it's so brilliant, because it's so subtle. What do we not see? We don't see an image of anatomy. We see a cartoon. In order to get an image of anatomy, you need pulse sound. So if you have pure continuous wave sound, you will never get an image of anatomy. The only thing you will get is your Doppler spectrum. Now, if you say, well, Sid, on my machine, I'm seeing both. Well, fine. Your machine is multitasking. It's using, some of the crystals in the probe constantly transmit, and a few other crystals are designated as full-time receivers, and all the other elements in the probe send out pulses to make an image. So this is, sometimes it's called a non-imaging probe, the Petoff probe. You look at it, you look at the end, and it's a circle cut into 2 semicircles, right? And that's, one is transmit and one is receive. I love this slide. Now the other kind of Doppler is called pulse Doppler. Now with pulse Doppler, what happens is the following. We have a little doodad on our screen called a sample volume. We can move it anywhere we want. And wherever we move it, we stop, and we then tell the ultrasound system, I want you to tell me what red blood cell velocities are present right here and nowhere else. And the system says, I can do that. What does it do? It calculates the go-return time of a pulse down to that sample volume and back. And then it sends out a pulse. Ping! Puts its fingers in its ears, becomes deaf, waits the exact length of time for sound to travel down to the doodad and back, opens up its ears for 1 millionth of a second, and closes them. If it hears something, it had to have come from the sample volume. Why? Because reflections from shallower depths, I had my fingers in my ears. Reflections from deeper depths, I put my fingers back in my ears. So the only place the data can come from is the sample volume or the gate. So the greatest advantage of pulse Doppler is range resolution. Depth, I've solved it. I know where the data is coming from. It is coming from the sample volume. Now, if you go back to my first lecture, let's think about it. How does the ultrasound machine measure the time of flight? Using the 13 microsecond rule, right? It uses the 13 microsecond rule. For example, if the sample volume is 3 centimeters away from the probe, then the go-return time would be 39 microseconds. Now, I told you that the speed of sound is the same for all sound waves in a given medium. How important is that now? If different frequency sound beams traveled at different velocities, or if different strength sound beams traveled at different velocities, none of this could happen. So the fact that sound travels exactly 1540 meters per second in the tissue is super important. And we adjust that receive gate. So here's a pulse Doppler. Here is our sample volume. Where are the red blood cells that created these Doppler shifts? Right here and nowhere else. Now let's look at the labels on a Doppler spectrum. Of course, the x-axis is always time. The y-axis is measured in terms of frequency, but the system calculates a velocity, and that's important to understand. We'll talk about that in a minute. We really measure a Doppler shift, so velocity is calculated, and sometimes things can hide when you do a calculation, and there's one thing that's important that we have to discover. All right, so we know the great strength of pulse Doppler, range resolution, but there's never only good news. So what's the bad news about pulse Doppler? There's an artifact. And the artifact is called aliasing. Now, simply put in plain English, an artifact is a is a second or a false identity, right? It's as if I could say, I'm not Sid Edelman, I am Carlos Santana, which would be cool. But anyway, that's the second identity. The second identity in pulse Doppler is that very high velocities look like they're coming from the opposite direction. And we've all seen aliasing. We've seen it when we've seen a Western movie. In every Western movie, there's a runaway stagecoach or a runaway chuck wagon. And as the stagecoach starts to move, the wheels go this way and the stagecoach goes like this way, and everything's fine. But then all of a sudden, as the wagon goes faster and faster and faster, all of a sudden the wagon wheels look like they're going this way, but the wagon is going that way. So that's aliasing. Very high velocities of the wheels going in one direction look like they're going in the other. So the question would be, why does aliasing occur in a movie? Because a movie is a pulsed event. A movie is the pulsing of images onto a frame so rapidly that it gives us the appearance of continuous motion, but it's not. It's pulsed. Anytime you see aliasing, you have a pulsed event. Okay. Now, aliasing occurs with pulse Doppler, never with continuous wave. It occurs with deeper sample volumes and with higher frequency transducers. Oh, big deal. Well, wait a minute, that is a big deal. Why? Because when we talked about axial resolution, we came to the conclusion that high frequencies give us better images, right? That gives us improved axial resolution. So we want to use high frequencies for imaging. But Dopplering hates high frequencies. Doppler wants low frequencies to avoid aliasing. This is gold. Doppler wants to be at 0 degrees with low frequencies. Imaging wants to be at 90 degrees with high frequencies. How cool is that? Okay, we see the difference. Now, what happens is, all of a sudden, someone just decompensates and starts screaming, I've reached a Nyquist limit. What does that mean? That means that they have observed aliasing. The Nyquist limit is the Doppler frequency at which aliasing occurs. And it's just like a speed limit. We know what happens when we exceed a speed limit. We get a penalty. We get a ticket. Well, when the Doppler shift exceeds the Nyquist limit, the penalty is that we see aliasing. So the higher the Nyquist limit, the higher the speed limit, the less likely we are to alias. What determines the Nyquist limit? Oh, our old friend, the PRF divided by 2. So let's go back. The PRF divided by 2. Shallow imaging, high PRF, high Nyquist limit, high speed limit, we don't get aliasing. Deep sample volume, low PRF, low Nyquist limit, low speed limit, I get aliasing like crazy. So this is why shallow sample volumes give us less aliasing and deep sample volumes give us more aliasing. So the Nyquist limit explains this. We haven't gotten to that yet, but this is explained. Okay? So that's what we know so far. And let's think about it. The PRF divided by 2 determines the Nyquist limit. What determines the PRF? The depth of my sample volume. Does anything else matter? No. Does the frequency of the transducer matter? No. Nothing matters. Just the depth of the sample volume. All right? So this is independent of everything else. This is what aliasing looks like. Here's my baseline. That's my Nyquist limit. That's my alias. Here, flow away from the transducer, and that's my alias. You know, we just point out, remember, aliasing never grows from the baseline. It always grows from the extremes of the spectrum. This is my perception of what's the problem is with aliasing. When we have severe aliasing, the signal wraps on itself. And when the signal wraps on itself, we have really limited the diagnostic utility of our study. I could even claim we don't even know the direction of flow. We certainly don't know anything about the magnitude of the flows, the velocities. So this is where aliasing really hurts us. So we want to get rid of aliasing. So let's talk about getting rid of aliasing. So in panel A on the left, what do we see? We see our Doppler spectrum in black, and we see our Nyquist limit in red, and that's my alias. So we have a collision between the spectrum and the Nyquist limit, and anything that exceeds that collision, that's my alias. Well, philosophically, if I could figure out how to shrink the spectrum, I can eliminate that collision. I'm not talking about slowing down the red blood cells. I'm just saying make the Doppler shift smaller for those red blood cells that are moving in at that velocity. The other way to get rid of aliasing would be to raise the Nyquist limit. So either panel B or panel C can be used to eliminate aliasing. Let's see how we can do that. First way to get rid of aliasing, heck, use continuous wave Doppler. It never aliases. So what we do is we poke around with our sample volume in different areas, different locations. We find the location where the velocity is the highest. Then we shoot a continuous wave Doppler beam through that region, and it'll sniff out the jet at that location. Next thing, select a transducer with a lower frequency because that will shrink the spectrum. This is the thing that most people sort of overlook, because to really observe it, you have to have frequency on the y-axis. It doesn't work if you have velocities. But what happens is this. If we have panel A, and we're using a 4 megahertz probe, and we have aliasing, and we do the exact same study with a transducer with half that frequency, the spectrum is going to shrink, because the Doppler shift is a percentage of the transducer frequency. So if the transducer frequency is halved, the Doppler shift created by red blood cells moving at exactly the same velocity is halved. So we shrink the spectrum and eliminate the collision. Now I put the line in, the red line is the Nyquist limit. Does that change? Of course not, it doesn't change. Same view, my sample volume's in the same place. My PRF's the same. Nyquist limit doesn't change. So this is a beautiful way of getting rid of aliasing. And again, imaging wants to be at high frequencies, Doppler wants to be at low frequencies. Great for exam questions. Okay, so again, if the transducer frequency is halved, the Doppler shift is halved. How else can we eliminate aliasing? Well, we get a new view. A new view, we move our transducer somewhere else where the sample volume is in the same anatomic location, but it's closer to the probe. And by doing that, my PRF will be higher, and that's, for example, using, looking at the aortic root from a suprasternal notch. The sample volume is 4 centimeters away from the probe instead of 20 centimeters away from the probe. So that's one way of raising our Nyquist limit. Now this is interesting. Increase the PRF by increasing the scale in the same view. Oh baby, how do you do that? How do you increase the PRF if you have the same view? This is mainly used in color, but it's something we should appreciate. Let's say we do our color and the PRF is like this. It's pretty high. That means my Nyquist limit is high. That means I'm not going to alias. So we sit there and we say, that's great when I'm looking at high velocities, but what happens when I'm looking at slow flows? When I'm looking at slow flows, they're buried in the baseline, right? Because if I have a high PRF, I have a big scale. So that means my sensitivity to slow flows is reduced. If we're looking at slow velocities, that hurts us. So what we do is we tell the system, I understand that you could do this. I don't want you to. I want you to do this. So the machine artificially has a PRF lower than its potential maximum. Okay? And what that does is it makes the system more sensitive to slow flows. Well, what happens if we don't change the settings back and now we look at high velocities? Now we're going to alias like crazy. So we say, oh, I've changed my mind. I don't want to be sensitive to slow flows anymore. So instead of doing this, go back and do this. So that's how we can increase the PRF. We can increase the PRF if the system was initially set up with a less than optimal, or less than a maximum PRF. And that's what we do when we change the scale. Now, once we get to the point where we're at full scale, the opportunity to do this goes away. That goes away. And lastly, zero baseline shift. Now, zero baseline shift. What happens is that baseline is in the middle. That's my Nyquist limit. That's my alias. So I have a button on the machine that can slide the baseline down, and essentially all it is changing the display. It's an electronic cut and paste. We take the bottom of the spectrum, put it up here. We take the bottom, put it down there. And now it looks as if the aliasing is gone. So if someone said, is the aliasing really gone? Reasonable minds could disagree. Some people would say, yeah, I don't see it. And other people would say, dude, you just changed the display. Of course it's still there. But this is important. First of all, if I make a measurement here, is it accurate? It is totally accurate. Okay? That's important. Number two is, I used to say this is silly and I would disrespect this choice. My feeling now is, if you have aliasing as it appears here, the first thing that I would do is use zero baseline shift. Why? Because you're not doing anything. You're not changing the probe. You're not changing the location, right? You're not changing the view. You're not changing the change of frequency. All you do is change the display. So that's really the first thing you do. That's the simplest thing to do. And on the echocardiographers boards, that's what's tested. That's the simplest thing to do. Okay, so those are the 5 ways to get rid of aliasing, and I would propose to you that you should know that. You should know those things. Now, this again is only a problem with what? With pulse Doppler, never with continuous wave. And then there are contrasts that we see now. With pulse Doppler, you can get away with 1 crystal because it can talk and listen. Continuous wave, 2 crystals. Pulse Doppler, range resolution. Continuous wave, range ambiguity. Let's just talk about what happens when you have a sample volume size different. Okay? Basically, you adjust the size of the sample volume by changing how long you listen. If the transducer does this, the sample volume is small. If the transducer does this, then the sample volume is elongated. So what do we have here? Here we have a sample volume in the center of a lumen of a vessel. Makes it a little bit easier to illustrate. And we have parabolic flow, which is laminar flow. So what streamlines are we going to measure with the Doppler? Just those. And if this is laminar flow, I get a spectrum and the window is empty, right? I have a clean envelope because I am only measuring flows at particular velocities. But what happens when my sample volume is big? Yikes. Now I'm listening a long time. If my sample volume is big, I'm measuring all kinds of different velocities, because with parabolic flow, the flow is fastest in the center of the lumen, and as you go toward the edges, it gets slower and slower and slower. Well, that means when I am measuring all kinds of different velocities, I'm going to get spectral broadening. I'm going to fill in the envelope, and that's what I get. Why is this important? It's important because if your sample volume is too big, your spectrum will mimic aliasing. Your spectrum will mimic turbulence. All right? You can have laminar flow. Your sample volume is big. You'll see it as turbulent. Spectral broadening. Now, what is the quintessential big sample volume? Continuous wave Doppler. And with continuous wave Doppler, your spectra are always filled in. They always look like there's turbulence there. So this is just one fact to know. And again, if the Doppler gains are too high, again, it will mimic turbulence. So you have to make sure your Doppler gain settings are okay. What do the grayscales of a Doppler represent? Well, we know that the x-axis represents time. The y-axis represents velocities or Doppler shifts. So what does the grayscale represent? It represents sort of the amplitude or the strength of the reflected signal. Another way to say that would be the concentration of red blood cells traveling at that velocity. And in these spectra, we would say that there are many red blood cells traveling at, let's say, 0 to 1 meter per second or 1 meter per second away from the probe. There are only a few red blood cells traveling at 2 or 3 or 4 meters per second towards the probe. So this tells us the strength of the reflection. Let's talk about color flow Doppler. Color flow Doppler is like double mint gum. You have 2 ultrasound machines in one. What happens is the ultrasound system sends out sound, puts it through an image processor, makes a grayscale image. Then it sends out other sound pulses, puts them through a color flow processor, which is simply a dictionary. And it says, look, if you're 4 meters per second towards the probe, you're red. If you're 2 meters per second away from the probe, you're blue. And it plops those colors onto a transparent sheet of plastic. And then the system superimposes the sheet of plastic on top of the grayscale image, and we have a color flow Doppler. Hey, look, we know the location of flow in this color flow Doppler. It's in the lumen of the vessel. Therefore, we know the location. This is range resolution. Depth, I know it. So therefore, color Doppler is a variant, or is based on pulse Doppler principles, and it is subject to aliasing. I wish I had a nickel for every time that's been asked on a board exam. All right? It's a form of pulse Doppler. For some reason, instead of calling it range resolution, you see terms like range specificity. Don't worry about the word. Is anything that tells you the location, it's pulse. Anything that tells you you don't know the location, it's continuous wave. So what do we have? There's actually a liver. It doesn't make a difference. What do we have? We have, this is our grayscale image. Here is our grays and blacks and whites. That's the anatomy. My transparent sheet of plastic. And here you have blues and reds. So, you know, we could make a joke, but it's not funny to you guys that the arteries are red and the veins are blue. Vascular surgeons love that. We don't believe that. We say flow towards the transducer is red, flow away from the transducer is blue. That's what the colors mean. But to figure out what the colors mean, absolutely, we look at the map. This map here, this is the dictionary. And by knowing the dictionary, that tells us what the colors are. So how do we look at a dictionary? Well, we look at a dictionary where we look where the black gap in the middle is. And we say these three words: no Doppler shift. Don't say no flow, because, for example, if we're at 90 degrees, we have no Doppler shift. And then all we do is look up, and we go towards. And whatever color we see, when we look up, that's the color that tells us that blood cells are moving towards the transducer. And then we go away. And whatever color or colors we see there, that represents flow away from the transducer. So that's what our dictionary means. Now we have different kinds of dictionaries. So let's do this one. The one on the left, no Doppler shift, red is towards, blue is away. That's just a direction map. Here, no Doppler shift, red, orange, yellow is towards, blue and light, blue and green are away. So what does this mean? Blood cells moving slowly towards the probe are red. Blood cells moving briskly towards the probe are yellow. Blood cells moving slowly away from the probe are blue. Blood cells moving briskly away from the probe are green. So this actually tells us the different velocities. Now, how do we tell the difference between flow reversal and aliasing? It's important. What happens when we have flow reversal is our colors move through the inside of the map. So the adjacent colors will be red, black, blue, looking at this map. Because we really have flow going forward, and then other places we have flow going backward. When we have aliasing, what happens is, I told you that aliases grow from the extremes of the spectrum. So the adjacent colors will be this one up here next to that one down there. So that's how we're going to tell the difference between aliasing and flow reversal. Okay? So with aliasing, the adjacent colors are from the very top and the bottom of our map, flow reversal through the middle. I always call that a rainbow. I like one-word things. If you see a rainbow, generally that's aliasing. So here we have a vessel during systole and diastole. What do we see? This represents red is flow away from the transducer. Not important which direction it is, but during systole, what do we see? Well, is this flow reversal or is this aliasing? Well, what are my adjacent colors? Red, yellow, white, light blue. Red, yellow, white, light blue. So this would be an example of aliasing. Now, other places, for example, in a carotid bulb, you would see flow reversal. This slide's super important. Doppler packets. When we do Doppler, color Doppler, the idea of sending out one pulse, listening for a reflection, measuring a Doppler shift, and calculating a velocity is way too simple. There's not enough data there to make an accurate determination of the Doppler shift. So rather than send out one pulse, the ultrasound system does the following with color Doppler. When it's doing Doppler, it does this. It goes, and it sends out a bunch of pulses. You don't have to know how many, 10, 20, whatever, a bunch of pulses. It makes multiple velocity measurements or Doppler measurements. And this can be done in like 1,000th of a second. And then it averages them. And by averaging them, we get a much more accurate representation of the Doppler shifts. So at that point, we would say, well, I want a big packet. That's called a packet or an ensemble. I want a big packet. True. Then you have accurate Doppler. But the problem is if you have a big packet, what happens to your frame rate? It goes down. So then you lose your temporal resolution. So this is like Goldilocks. Too much, too little, just right. You don't want to have the packet so big that your temporal resolution is poor. You don't want the packet so small that you don't have accurate Doppler. You want it to be just right. Okay? Now, because of this phenomenon with packets, color flow Doppler measures mean velocities, whereas pulsed and continuous wave measures peak velocities. I would put a star next to those two statements. That's a very, very heavily tested concept as well. And this is because of the packet. Now, this loop is what I showed you with temporal resolution. Now, let me explain how it was created. The image on the left is just a grayscale image. All you need is one pulse per line. Okay? So the system does this. Done. Okay? And it can do that maybe 120 times a second, so you get a real high frame rate. The loop on the left, the line that's blue, tells you and me that color is on. So this image is a color image. But I turned the color off because I didn't want you to be distracted by it. So what did we do here? Well, here I have colorized the universe. Right? Every single scan line now has color Doppler pulses going down those lines. In fact, a packet of them. And it's imaging. The color Doppler is to the bottom of my display. So now I have used as much time as possibly could be used to make each image. Because the system, let's say the packet size is 10, would do this. That takes care of the image. That's easy. But then the packet. Then image. Then packet. So what happens is, essentially, if my packet is 10, it would take 10 times longer to make one color Doppler image than it does a standard anatomic frame, which means your frame rate is only a tenth as much. And when your frame rates are low, you lose short duration events. It's a bad thing. So what can we do? Take-home message, and I'm sure you'll hear this many times from people who are smarter than me, is you can do whatever you want when you're looking. But when you're making measurements or a diagnostic study, what are you going to do? You're going to pull the sector in to look at only the region of interest. You're going to pull the bottom up so you don't waste all that time sending pulses to depths that you don't care about. And by doing this and doing that, you can colorize maybe 1/30th of the full image, and your frame rate goes way back up. So there's a very important practical nature to this, and that's, I think, one of the reasons why it shows up on the test. Okay, now I'm a creature of habit. So I look at my color map. Now, again, in cardiology, it's not that important because it's always red towards blue away. I look at my color map. So what do? I say, okay, no Doppler shift. No Doppler shift. Towards purple, red, yellow. Away, purple, red, yellow. Oy. The colors are the same. What is going on here? Well, clearly, I have voluntarily given up my direction information. I don't care whether I have a positive Doppler shift or a negative Doppler shift. All I care about is whether I have a Doppler shift. Why would I do that? Why would I give up that information? The reason is because if I'm willing to give up the intensity level of the processing of the Doppler signals, I get a much more sensitive Doppler. But I get less information. This is called power mode or energy mode or angio mode. Here, all we're doing is listening for a Doppler shift. If there is a Doppler shift, we plop color there and we're done. And by doing that, we have tremendous fill-in. This is great for LVO pacification, right? With Doppler and all of these things, because it's much more sensitive. So that's why we use power mode. Lose it, because a lot of times we don't care what the direction is. Nice thing. And again, the most important thing is that it has an increased sensitivity. And it really does look like an angiogram. Spectral analysis. What is spectral analysis? Spectral analysis is like going to a restaurant with a gourmand. A gourmand orders a bowl of soup and tastes it and then lists out all the ingredients, as annoying as that is, right? They sit there and say, oh yeah, it has a hint of saffron and a touch of basil. Well, that's spectral analysis. It is the study of a collection. What is the collection that we are talking about? The collection that we are talking about is we get reflected signals not off of one red blood cell, but many red blood cells, right? Even in a small sample volume, there are a lot of red blood cells, and certainly with a big sample volume or continuous wave, we have tons of Doppler reflections. So it's a complex signal. Mathematical techniques have been created where we can separate the complex signal into its components. So that can tell us what individual velocities are present in that signal. And that is called spectral analysis. Spectral analysis technique used for spectral Doppler, which is pulse and continuous wave, is called the FFT, or the fast Fourier transform. The reason why we use the FFT is because it is accurate. Strange that it has the word fast, but we use it because it's accurate. For color flow, we cannot use the FFT, in part because there's so much Doppler data that the FFT is not fast enough. So instead of using the FFT, we use something called autocorrelation or correlation function. So know which technique is used with which. I know that there's at least one engineer in the audience because I was having breakfast with her. So for those of you that engineers, regular people don't have to know this, the FFT is done in the frequency domain and autocorrelation is done in the time domain. But you don't have to know that. Okay, so understand those. And these things break the complex signal into their components. In the early days of Doppler, all we got is a line. That's all we had was a line. And it represented the mean velocity, and that was it. Now we have all the different velocities. A question: can a patient be so severely anemic that you cannot perform a Doppler exam? The answer says within the physiologic range, the concentration of red blood cells is always sufficient to perform a Doppler exam. So, of course, the hemodynamics are going to change because when a patient is anemic, velocities are higher and many other things. But never say I couldn't do the exam because the patient was so anemic. There can be other technical limitations. However, there is always enough of a signal to perform a Doppler. Doppler artifact. This is cool. And this is, if I was writing the test, this is what I would do. So what do we have? Look what we have here. Here we have colors outside the lumen of a vessel. I know that there is not red blood cells moving there. This is created by what? By tissues moving, right? The tissues move, we measure a Doppler shift, bingo, we colorize it. So we want to get rid of this. Sometimes this is called ghosting artifact. We want to get rid of this. So how do we get rid of it? Well, let's think. This, if I get my cursor back, here. This represents Doppler shifts off of red blood cells. They move fast. This represents blood cells. This represents Doppler shifts off of moving tissues. They move slowly. So if I can preferentially tell the machine, look, don't put color where the velocities are low, I'll get rid of the artifact. So everybody look. See that says no Doppler shift right there? Red is towards, blue is away. But I click on something called a wall filter. Here's the wall filter. Now I'm saying no Doppler shifts towards and away. But I'm saying if the velocities are slow towards the transducer, don't put color there. If the velocities are slow away from the transducer, don't put color there. So what am I doing? I'm selectively decolorizing the slow velocities. What are the slow velocities? The signals off of the tissues. So that's called a wall filter. And of course, when we get color flashes inside the myocardium during contraction, you hit the wall filter, they go away. So know about the wall filter. What's interesting is there's someone here who's probably saying, What happens if I lower the color Doppler gain? Well, if you lower the color Doppler gain, you are not discriminating between fast and slow. You're discriminating between strong and weak. What makes great reflections? Tissues. What makes weak reflections? Blood cells. So if you go ahead and you lower your Doppler gain, you get this down here. That's what you get. All right? Because you wipe out the weak reflections, which are from the red blood cells. And the reason why I would put this on the test is, guess what that's the basis for? Tissue Doppler. If you say, I only care about the strong reflections, you're getting them off of red blood cells, and that is the basis of tissue Doppler. Sometimes this is called a high-pass filter, and the wall filter, the use of that or the strategy is the fundamental basis for tissue Doppler. That's about it. So as always, it is a great honor to be with you. It's a great honor to be with a faculty like this. Thank you very much. And I'll be around during the day if you have any questions.
So Sid, just a couple questions. What is a color variance map?
I didn't go over the color variance map. Most labs don't use it. What happens is, when I showed you color maps, I showed you that the towards color was up and the away color was down. Because of the packet and making many, many different velocity measurements, scientists and engineers said, I'm going to look at the variability of those 10 individual Doppler velocity measurements that were made in 1,000th of a second. And if those variability was narrow, that was laminar flow. And if the variability was great, that was turbulent flow. So that theory is correct. The problem was that the people didn't know. They went like, how am I going to display this? I can't use blacks and whites and grays because that's anatomy. I can't use up and down because that's towards and away. So what they did was they invented variance mode where they split the color bar from the left side to the right side. So if you see a map that has different colors on the left side and the right side, that's a variance mode. The left-sided colors are the laminar colors. That's easy. L is for left, L is for laminar. The right-sided colors are the turbulent colors. So that's how we can see whether we have laminar or turbulent flow within a color Doppler. Now, many of the people I work with, certainly the vascular people, they say, I don't care, because I'll just drop a sample volume in there. I'll look for spectral broadening on my pulse Doppler. Don't bother me. So some people use it. I know the people, Duke uses it, right, David? Duke uses it, Texas Heart does not, but that's what variance mode does. It gives you another discriminator, which is laminar or turbulent flow based on the left and right.
And two more brief questions. Some of the other questions that were asked, David Adams will cover in his next lecture. But does Zoom affect resolution?
Does Zoom affect resolution? That's a nasty question. The answer is yes and no. Let me explain. There are essentially two kinds of zooms. One kind of zoom just says, I'm leaving the data where it is, and all I'm going to do is take a region of interest and blow it up. Well, if you blow it up, it's pretty clear that each little part of the image is bigger. So the image looks sort of blocky or grainy. But technically, the resolution hasn't changed. On the other hand, there's some kinds of zoom where that's called read magnification, by the way, where you keep the data. There are other times when what you do is you actually flush the data out of the system and you rescan only the region of interest. If you rescan the region of interest and collect new data and you're imaging shallower and you're imaging a smaller area, then you do affect resolution. All right. So when we talk about this for boards, many times there are areas where they don't address it because it's sort of kludgy. You know, does read zoom, where you just use the old data, does it change the resolution? The technical answer is no, but it sure changes the way the picture looks. The picture looks lousy. So if this is based on some level of apprehension about it, the times when that question is asked, it'll be clear that there's an answer yes or no, and when it's equivocal, you won't see it.
And one final question. I know we're a little bit over, but if you have aliasing, can you add the stuff above the baseline to the stuff below the baseline and get a total number.
The question was, if you have aliasing, can you add the stuff above the baseline to the stuff below the baseline and get an accurate measurement? Remember I said, that's what zero baseline shift does. You can absolutely do that. So there's no problem doing that. What's the problem? Once you wrap around, you don't know what you have. But before that, absolutely kosher.
Okay,
Thank you very much.
I think we'll move on, and thanks again to Dr. Edelman.